All right, welcome everybody. This is 8.3. We're solving exponential equations. So a lot of the things that we've done before for solving, like when we did radical equations and rational equations and all the things that we do for solving still applies. So a lot of the things we're doing is like PEMDAS backwards. We're going to add or subtract first, multiply, divide next exponents. Again, exponents are really related to logs, so kind of the opposites of bases is their logs, and logs is bases. So if that doesn't make any sense, it's okay. We're going to go over some things with that, okay? And then, yeah, let's give it a go. So one thing that's helpful isn't necessarily required most of the time, but sometimes it's helpful is if you see like bases, like for example, 1, we can use its opposite. We can use log base 2 on both sides, and those would cancel. So we'd end up just getting x equals 4, which kind of makes sense. If the bases are the same and all that's different would be the exponents, then those two exponents have to be the same. So if we look at example 2, x would have to be 9, right? I kind of changed this. I'm going to put this back. I think on yours it's just an x, which is just fine. So this would be 6, okay? But when we look at the next example, they don't have the same base. So one of the things that we can do that can make it a little easier is if you can find a common base. So if this has a base of 2, could we make 4 have a base? Another way to say that is 2 to what power is 4? So we could do 2 squared. Okay? So that we haven't changed anything. We've just basically unsimplified. And now we have a common base. So we have to kind of go back to our first lesson where if we have a power and a power, an exponent on an exponent, then we can multiply those exponents. So this would be 2 to the x equals 2 to the 12. So then we could just say that x equals 12. Does that kind of make sense? So see if you can kind of come up with a common base that you could use for both sides. Let's try a couple more examples. So if we're going to do D and C. So looking at B, we have a base of 3. That can't be changed at all, right? There's nothing else that we could reduce that for. But with the 81, could we rewrite that as 3 to some sort of power? Yeah. Again, we're basically saying 3 to what power is 81. And we've done that before. So this one would be, so I don't need to get rid of that. This would be 4, because 3 to the 4th is 81. So now we have a common base. That means that x has to be 4. Again, the reason why we can cancel out those 3's is we would use log base 3 on both sides. Okay? Those would just cancel. All right, let's try that last one for C. Sorry, my tablet is trying to be charged at the same time, and it's kind of glitchy when it's like that. Okay? So again, we'd want to have a common base. So we already have a base of 2. Could we make this be a base of 2? Of course. 2 to what power is 8? So that would be 3. So I'm just kind of talking to myself, just all by myself, just going over this lesson. All right, so here we go. Again, this is 2 to the 3 times 4, which would be 12. So that means that we could do log base 2 on both sides. We've got 2x equals 12. So what would x have to be? Well, we could just divide both sides by 2, and we'd get x equals 6. All right, we'll have a couple more, maybe one more example of that, or two. But most of the time, we'll probably go and do this a little different. So here I'll give you an example where we could do it 2 different ways. Okay, so if we're going to solve Again, we're kind of following that same PEMDAS backwards, order of operations backwards. So we would want to add 2 to both sides first before we try and get a common base. So at this point, again, we'll have 2 examples. One where we have a common base and one where we don't. Okay, and sometimes you won't even have the option to have a common base. I'll give you an example of that coming up. So a common base, again, we want to think what number could we multiply multiple times that could give us 16, and also multiply multiple times to give you an 8. So here it would have to be a 2. 2 to what power is 16? I think that's a 4. And on the right side, 2 to what power is 8? And that would be 3. So here we'll end up getting 2 to the 12x is equal to 2 to the 3. So we can do log base 2 on both sides, and we'd get 12x equals 3. And then we could just divide both sides by 12. On your homework, I think it's going to require you to do it as a decimal. So 3 over 12, or 1/4, is 0.25. All right, so let me show you the other way. This is when you don't have a common base. And again, the only reason why when you actually really need it is when you have x's on both sides. And I'll give you an example of that. So here is an example where we don't have to have a common base. We could get rid of that 16. Again, we're just trying to get x by itself, so let's get rid of the 16 by using its log. So we'd get 3x is equal to log 16 of 8. And then we would just divide both sides by 3. So here you would need to be able to type that into your calculator. Again, if you have a TI, I think you do math, and then we go up a couple times, and you should see log base. If it's a Casio or using one of the blue calculators, usually there's just a button for that. Or if you're doing a graphing Casio, I can't remember, so just go, you can come and talk to me, or you can go look at our previous videos that we go over that, or the filled in notes. I think I have it written it down. Okay. Oh, I think it is. I have it right here. I think it's in, well, kind of wasting my time. So I'll go back to that if you need to. Okay, come talk to me. So when you type that all in, again, make sure you put it as a base of 16. Okay. Why don't you give that a try real quick if you haven't. Sorry, I'm just pulling it up so I can speed this up a little bit on our video. Okay, sorry about that. So here, okay, there we go. Well, I guess we should know either way. It should give us 0.25 because it's the exact same equation, right? We're just solving it a different way. Okay. All right, let's go and try some others. Hopefully this will go a little quicker. So if we're trying to get x by itself, again, I'm just going to use log base 27. Again, you could get a common base if you wanted to, but log base 27 on both sides. So 3x is equal to log base 27 of 81. And then we could just divide both sides by 3. If you give that a try, see if you can get that. I end up getting 4/9. or we'd probably want to have it as a decimal. So if we 4 divide 9, be 0.44. Okay. For b, let's give this a go. We'll do log base 3. So negative 2x plus 2 should be log 3 of 81. And then next we'd want to get this 2 away. Sorry, just make sure we put parentheses around that 81. Otherwise that subtract 2 might end up inside. Okay. So now we've got negative 2x is equal to log 3 of 81 minus 2. And then our last thing would be to divide both sides by negative 2. So be careful when you do this. Sometimes people will type it in like this. And if you type it like that, order of operation will have you do that first. But we're not just dividing the negative 2 by a negative 2. We're dividing everything by negative 2. So you need to either put a parenthesis around that, or you could use the fraction button on like a Casio and type it in so it looks just like this. Or for a a TI, we push alpha, and then we push y equals, and then enter. That will do a fraction as well, okay? At least for an 84. Okay, so we'll type that into our calculator, and we should end up getting negative 1. Okay. All right, let's keep going through this. Again, here is an example where we have to have a common base. You could probably do it differently, but I think it gets more complicated. So a common base, we have a base of 2. This is a base of 4, but we can make that 4 become a base of 2 by doing 2 squared. So watch careful on this one, because when we have an exponent on an exponent, we multiply those exponents. So this will become 2 to the 2x plus 2. It's like the distributive property. So 2x plus 2. Now we can have a common base of 2, so we can do log base 2. So 3x is equal to 2x plus 2. And then we'll just have 2 steps. We'd subtract 2x. So x equals 2. I guess it's just one more step, okay? All right. We'll skip D. If you want to look at that when I have it filled in on Canvas, on the filled in notes. Same here. We're only going to do, I guess, most of those. But if there's any others, you can always look at those, okay? So going to this point, we can't, like this example, we cannot have a common base, right? We can't rewrite this as 3 to some exponent that would give us a 30. Our answer is going to end up being some sort of decimal, and that's what we're going to come up with, but we're going to need to use logs to do that. So we'd do log base 3, and we'd get x equals log base 3 of 30. And we just want to put that into our calculator and see what you get. We should end up getting 3.10. So again, round to 2 decimals. If you have any questions, stop by. Okay, we'll skip B. Let's go to C. Sorry, my script. My videos are probably crazy because I'm going all over the place. Okay, but again, here we go. PEMDAS backwards. So what would we do first? We would subtract. So we'd get 14. And the other side, 2 times e to the 2x. 4 times e to the 2x. Next, after adding or subtracting is multiplying and dividing. So this 4 is being multiplied. So we'll divide both sides by 4. We can either leave it as a fraction, or you can see if you can reduce it. If the decimal keeps going forever, then you're going to want to keep it as a fraction. So this one I think ends up being 3.5. So you could have it either way. Next, we'd want to get rid of the e is using a natural log. So 2x equals the natural log of 3.5. And then our last thing would be to get rid of that 2 by dividing. So we'd put that into our calculator, and we should end up getting 0.63. Okay, so I encourage you maybe to pause and type these in. Make sure that you can type it into your calculator. This one's very similar. It's just a base of 10, so we'll still add 2, or add would be our first step. Next, we want to get rid of the base by using its log. And it's just a log base 10, but we can just use log. And then our last thing would be to divide both sides by -2. And then we would round to -0.45. All right, last two. This one is pretty much probably as hard as this can get. We have, I think, maybe 4 steps. Okay, so we could not add Mr. Warner. We would subtract 5. So we'd get 81. Next, we'd want to get rid of the base by doing its log. So 5x minus 3 is equal to 81, log. If you realize that that can be simplified, you could do that really easily. So again, it's 9 to what power is 81? So this is just really 2. But if you weren't sure, you could just leave it in your calculator and see what you get. So we get 5x minus 3 equals 2. And then we've just got those last 2 steps. So add 3. And then divide both sides by 5. So x equals 1. All right, hopefully that was okay for you. Again, on your homework, make sure that if it says to round to the hundredths, make sure you round your answer to the hundredths place. All right, our last example here real quick is this one's a kind of special case. So if we were to subtract 19, we would get -15 on that side. Okay. Next, we would do log on both sides. So we'd end up getting x minus 7 is equal to log of -15. So here again, we need to remember that a log puts out exponents. This is saying 10 to what power is -15. And it doesn't matter how many times you multiply 10, it's never going to be negative. So we shouldn't have an answer here. This would be a D and E. Does not exist. All right. Well, if you have any other questions, please stop by, and we'll see you later.